What happens when we're trying to implement integration by parts and both pieces of the function, well, it's kind of hard to guess which one you should use as the u and which one you should use as the dv. What would you do in a situation like this? I have e to the 3x times cosine of x. I want to integrate that with respect to x. And so it turns out it doesn't matter as long as you're consistent and keep up with that same setup. So for what I'm going to do in this case here is I'm going to illustrate what happens as we run through this process of integration by parts. Ultimately, I want to get back to this integral. And so we'll see why in a little bit, but I'm just going to call this thing as if it were an algebraic variable. I'm just going to call it I right now. So of course, following our typical setup, I'll let u equal my e to the 3x function. My dv term is cosine of x, so naturally, or dx, there we go. So naturally my v term is just sine of x, and then for my du, from chain rule, I get 3 e to the 3x dx. And so, following our typical uv minus integral of v du setup, well, the uv part is pretty straightforward. We have e to the 3x times sine of x. Well, that's not much of a surprise. And of course, this is all equal to our integral. And then, of course, minus integral of v du. But this is not quite the same as we had for our original integral. This is now a sine function as opposed to a cosine function. And so, I will admit, it may seem intuitive to try and switch, what you had as the u and what you had as your dv term. However, if you do that, you're actually going to just undo this step and get back to the original integral itself, which integral equals integral, I equals I. That doesn't actually tell us what the antiderivative is. And so, even though it may not seem like it, let's keep pushing forward. And so I'm going to keep my e to the exponential as the u term. I'll keep my trig function as the dv term. So of course, I'll take my derivatives here. Chain rule going on there, so I've got now 9 e to the 3x. My v function is now just negative cosine, so I'm going to have to keep track of those negative signs as I'm running through my process here. So of course, our original integral was e to the 3x sine of x minus this new integral. So I'm just going to throw in some giant brackets or parentheses, whatever I need here. So I've got, so again, uv, so that's minus 3 e to the 3x cosine x minus, again, just from the regular setup, integral of v du. So v is negative cosine, du is 9 e to the 3x. And so, I'll agree, this looks messy right now, but before we do anything, I'm going to start dealing with all these negative signs, trying to clean things up as much as possible. Alright, so obviously minus and minus here clean up. And then I've got minus, 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 so that'll just be minus then. Minus 9, I'll pull that coefficient out in front, times the integral of e to the 3x times cosine of x dx. Well, remember, we're setting this whole thing equal to our integral I, but remember, I was the integral of, oops, let me back up here. I was the integral of e to the 3x times cosine x dx. And so, in being consistent with our integration by parts, that same integral has shown up again in our steps here. And so what this means then is I can go ahead and just substitute that part for I. And now I've got what looks like a typical algebra equation, because I've got 9 times my integral, so I've got 9 times I here. And so now I'm just going to solve for I by itself. Let's see, I add 9 back over. I've got 10I. And so I have e to the 3x sine x plus 3 e to the 3x cosine x. All of this equal to 10 times I, so I'm just going to divide everything through by 10. And that gives me my value of I by itself, my antiderivative for this thing. And of course, plus C. And so this is a technique where we, as long as we're being consistent with our integration by parts, if we are able to regenerate the original integral itself, we can now use this as an algebraic setup in order to find our antiderivatives, which is themselves really cool.